Assalamu alaikum. Hi everyone. In this video series, I would like to share with you the basic concepts of the arithmetic circuit designs, mainly the adder and subtractor. And we will also cover the concepts of multiplier circuits in the later part of this video series. First of all, the term arithmetic that I've mentioned is in fact refers to the basic arithmetic operations consisting the addition, subtraction, multiplication, and division operations. By the way, the design of the circuit that performs the division or so-called the divider circuit is beyond the coverage of this video lesson. So now we are going to focus on the digital circuits design for the three arithmetic operations, namely the addition that corresponds to adder, the adder that corresponds to addition, subtractor that corresponds to subtraction, and multiplier that corresponds to multiplications. When we are thinking of designing a digital circuit that perform one of these arithmetic operations, our mentality or the way we think must be looking the calculation process in the binary world. In other words, the circuit is designed based on the operation between binary numbers. Let's begin by looking at the circuit design for an adder. Now let's consider adder circuit, which corresponds to the addition. Before we're thinking of adding large numbers that require large size of binary digits, or we call it bits, the word binary, the word bit is actually comes from the word binary digit. So they combine like this with this, so they get bits. Like 8 bits, 32 bits, and so on. So let's begin with considering an adder that adds 1-bit numbers. Imagine that we have two 1-bit numbers, namely A and B. So let's write y equals to A plus B. Here A and B are 1-bit numbers. A and B are the inputs and y is the outputs. Here I avoid to use the plus signs, these signs to avoid confusion with the logic or operation, because mostly we use this to represent OR. Okay, so most of the time I prefer to write the word plus to represent the addition, but sometimes I also use this symbol to represent addition. So to understand certain symbol, we need to know the context of the process. Then let's construct the corresponding truth table with the columns A, B, and Y. Since A and B are 1 bits, so they are either number 0 or 1. And here are the combination between them: 0, 0, 0, 1, 1, 0, 1, 1. Now y is the sum of A and B. Obviously, this gives 0 plus 0 gives 0, 0 plus 1, 1, 1 plus 0, 1, and 1 plus 1 equals to 2. Okay, writing y in the binary representation, we replace this with 1, 0, 1, 0, and let others fill with 0. Here we know that even though A and B are 1 bit, y is not 1 bit, because the largest value of y is equals to 2, which is 1, 0, that is 2 bits. So it is like y has 2 subcolumns. So let's name each column with index. So this is y1 and this is y0. Now let's find the logic operation between the output y and the inputs a, b. It is easy to see that from the truth table. From the truth table, y1 equals to a and b, and y0 equals to a, x, or b. Thus, the circuit is simply consists of two gates like this, where this is a, this is b, this is y1, this is y0. Actually, there are specific names for the output. y0 is called the sum, often denoted as S, and y1 is called the carry, often denoted as C. Okay, now let's think of adding bigger numbers. Let's say 5 plus 7, which equals to 12. In binary, we represent this as 101 plus 111. Then we add these numbers column by column, starting from the right. So in the rightmost column, we get 1 plus 1 equals to 2, which is 1, 0 in binary. In which the sum is 0 and the carry is 1. Then the next column gives 1 plus 0, which includes the carry from the rightmost column, that gives also 2. And finally, 1 plus 1 gives 3, which is 1, 1 in binary. So the carry in the leftmost column, this one is transferred to the answer and become part of the answer. Obviously, the answer is 1100, which equivalents to 12. Of course, this calculation is very easy and straightforward. But our interest is not about getting the answer. Here we are interested to know the process of calculation, how the input is processed, so that we will be able to design the circuit. So now, let's see, is it possible to utilize multiple numbers of this 1-bit adder? Is it possible to utilize multiple number of this that we have here to perform this multi-bit operation 5 plus 7? Let's take 3 units of this adder and cascade them in this manner from right to left, Here we have, because A and B now are 3 bits, so here we have A2, A1, A0 equals to number 5, which is 101. So A is 101. And B is number 7, which is 111. Then the rightmost column, this, produce 1 plus 1 produce 2. So the sum is 0, the carry is 1. So the carry out from this rightmost column need to be fed to the next column to realize this algorithm, to realize this. But this is impossible because the input is already full. This input is already full, occupied by A1 and B1. Thus, we need to have an improved adder which can afford 3 inputs, namely A, B, and carry in. Okay, now the truth table of the new adder should be like this. Its input are A, B, and carry in. Thus, we have 8 possible combinations between the inputs. The outputs, let's again call it Y, is the sum of these 3 variables, A, B, C in. So the first row gives 0 plus 0 plus 0, which is 0, and then 1, 1, 0 plus 1 plus 1, 2, 1, 2, 2, and finally 1 plus 1 plus 1 equals to 3. Okay, Y is again 2-bit because when we express this in terms of binary, number 2 is 1, 0, number 3 is 1, 1, and let the others fill with 0. So Y again is 2-bit, so we can denote this as Y1, and this column becomes Y0. Or more specifically, we call Y0 as the sum, or simply so this column is sum denoted with S, and this column is carry out, C subscript out. Now let's use K-map to obtain the Boolean expression for carry out and sum. So by filling out this K-map, I get 1, 1, 1, 1 here for carry out, and 1, 1, 1, 1 for sum. Okay, and then we form the groupings, 1 here, 1 here, 1 here, and then individual group for the ones in S. Okay, so I have carry out equals to AB or AC in or BC in. S is a little bit longer, A bar B bar C in or A bar B C in bar, or A B C in or A B bar C in bar. For instance, if we stick with this sum of products form, the circuit of this new adder is like this, you know. So this bubble represents the inverter, and this is A, B, C in, and this is the sum that consists of 4 AND gates and 1 OR gates, and this is carry out, consisting 3 AND gates and 1 OR gates. Okay, this adder is in fact known as the full adder. Often symbolized with FA, and the previous adder, this one, is known as the half adder. This is known as the half adder. Symbolized by HA. The half adder can still be used when we only need to add 2 inputs without the presence of carry in. By the way, the full adder here is more prominent than half adder due to its ability to receive a carry as the input. Okay, now let's inspect the Boolean expression for carry out and sum of the full adder again. Here are the expression for sum and carry out. the expression for sum is in fact can be written in a more compact form, such that this in fact equals to A XOR B XOR Cin. Okay, I leave this to you to prove the equivalence of this expression using perhaps some Boolean identities. The expression of carry out can also be presented in an alternative form. For example, if we break this group and this red group and let this one become alone and also this one, we can rewrite the Boolean expression such that we have A bar B carry in, A B bar carry in. So I replace this with or A B bar carry in or A bar B carry in, and factorize carry in from the last two terms. I get this, and this is equivalent to A XOR B and Cin. Okay, using these alternative expressions of carry out and sum, we may draw an alternative circuit that look like this. Okay, here we require five logic gates to realize the full adder, as compared to 9 gates excluding the inverters in the previous style. By the way, both of them are full adder that perform the same job. Okay, now let's redo the addition. 5 plus 12. Sorry, 5 plus 7, which is equals to 12. This time, we are going to use the full adder. Before that, I prefer to label the carries on the right side and the left side like this, rather than labeling them at the top. Rather than labeling carry at the top and at the bottom. So this is the same full adder. The only thing that is I just redraw it in different style, but they are totally the same circuit. Alright, to realize 5 plus 7, we require 3 units of full adder. So we take 3 full adders like this and cascade them like this, okay, from right to left, and we do this connection. That is, the carry out from one column is transferred to the next column, and similarly here. Now let's assign, so this is our A2, A1, A0, B2, B1, B0. We also can denote the carries with index. The rightmost is C0. Okay, do not get confused with CO. This is C0. Then C1. This is C2. And this is C3. Now A equals to 5, which is 1, 0, 1, and B equals to 7, which is 1, 1, 1. The carry in at the rightmost is of course 0. This is of course 0. And then we process the output such that we attain 1 plus 1 here equals to 2. So this becomes 1, this becomes 0. Then 0 plus 1 equals to 2 again. 1, 0. And finally 1 plus 1 equals to 3, which is 1, 1. Okay, notice that C3 here becomes part of the answer. So this one from the leftmost column, the carry-outs of the leftmost column are transferred and become part of the answer. Okay, and finally the answer is this 1, 1, 0, 0, which equals to 12. This particular multi-bit adder is known as the ripple carry adder because the carries are transferred from one another, like the motion of ripples. Okay, for simplicity, we often present the full adder and half adder as blocks. Okay, here are the block diagram of the 3-bit ripple carry adder. Okay, so instead of drawing the internal architecture, the internal construction in detail, we just represent the full adder with block. So this is full adders. Okay, and then we do this connection, and this is part of the answer. Okay, similarly we have here this is A2 A2 sorry, I can use different color perhaps. So A2, A1, A0, B2, B1, B0, C0, C1, C2, C3, and the bottoms are actually S0, S1, and S2, and these are the answers. Okay, alternatively, since the rightmost carry-in is always 0 in addition, we can also use the half adder. For the rightmost bit slice, okay, additionally 1 unit of full adder or half adder in multi-bit adders is called a slice of adder. So this is 1 slice, this is 1 slice, another slice, and another slice. So the number of slices depends on the range of the input values. If we need to add bigger numbers like more than 100s or 200s, maybe we require 8 bits adder to perform the task. Moreover, in practice, we often need to consider sign numbers that involves positives and negative values. This factor also influences the number of bits or slices. So as designers, we need to know the requirements in realizing a computation before we proceed with the design.